Hello and welcome back. Let me open tonight with something true about the last time you stood in sunlight. The warmth you felt was old, not 8 minutes old. That's only how long the light took to cross from the sun's surface to here. The energy behind it was released in the sun's core a very long time before that, and then spent an enormous span of time working its way out. At the center, where hydrogen is fusing into helium, the material is so dense that a photon travels only a tiny distance before colliding with something and being absorbed and re-emitted in a random new direction. Then again and again, millions of times over, taking a stumbling, aimless path outward. Estimates for how long that journey takes vary considerably, depending on the assumptions, but they're generally in the range of tens of thousands to a few 100,000 years. So the energy warming your face on a summer afternoon was released around the time our species was learning to make sophisticated tools, and it has been jostling its way to the surface ever since. And here's the second thing, which is really the subject of tonight. That process, the fusion at the core, the slow leak of energy outward, is the sun dying, not a metaphor. A star shines by consuming itself, and every photon that leaves is a small portion of its life spent. Shining is dying. There is no other kind of star. So every point of light above your roof tonight is in the process of ending. Most will take billions or trillions of years about it. A few will take only a few million more. And what each one becomes at the end depends almost entirely on a single number: how much material it started with. Tonight, we'll follow all of the paths slowly, with nothing for you to remember and nowhere to arrive. Let's define the thing properly, because the whole of tonight follows from one simple picture. A star is a contest between two tendencies held in balance. Gravity pulls its material inward. An object with the mass of the sun has enormous weight bearing down on its center, and left to itself, that weight would collapse the whole thing. Pushing outward is pressure, from gas that is extraordinarily hot, and from the radiation streaming through it. That pressure is maintained by energy released in nuclear fusion at the core. When the two balance exactly, the star is stable. Every layer sits with the weight above it matched by the pressure below, and nothing moves. That state is called hydrostatic equilibrium, and it's why the sun has looked essentially unchanged for 4.5 billion years. The balance is also self-correcting, which is why stars are so steady. If the core were to contract slightly, it would heat, fusion would speed up, pressure would rise, and it would push back out. If it expanded, it would cool, fusion would slow, and gravity would pull it back. A star is a thermostat that regulates itself. So the entire life story of any star is the story of that balance being maintained. And the entire death story is what happens when the fuel that maintains it runs low. Let's look at the fusion itself, because it's stranger and slower than most people expect. In the sun's core, at about 15 million degrees, hydrogen nuclei, single protons, fuse together in stages, eventually producing helium. The most common route is called the proton-proton chain. 4 protons ultimately become one helium nucleus, and the helium weighs slightly less than the 4 protons did. That missing mass, about 0.7%, becomes energy, according to the most famous equation in physics. The sun converts about 600 million tons of hydrogen into helium every second, and loses roughly 4 million tons of mass in the process, radiated away as light and neutrinos. That sounds enormous, and it is, but the sun is enormous too. At that rate, it can continue for about 10 billion years before the core runs low, which is why we've had 4.5 billion years of stable sunlight and have 5 billion or so to come. And here's the detail that surprises people most. The sun's energy output per unit volume of its core is small. A cubic meter of the solar core produces less power than a compost heap of the same size. The sun is bright, not because the fusion is intense, but because there is so very much of it. That slowness has a specific cause, and it's worth a chapter, because it's why we're here at all. For 2 protons to fuse, they must come close enough for the strong nuclear force to take hold. But both are positively charged, and they repel each other fiercely at short range. At 15 million degrees, the protons simply aren't moving fast enough to overcome that repulsion. Classically, fusion in the Sun should be impossible. What makes it happen is quantum tunneling, the fact that a particle described by a wave has a small probability of appearing on the far side of a barrier it hasn't the energy to cross. Rarely, but not never. Then there's a second bottleneck, and it's the tighter one. When two protons do meet, they don't stick. A pair of protons isn't a stable nucleus. For the reaction to proceed, one of them must convert into a neutron at the moment of contact, which requires the weak nuclear force. And the weak force is called weak for good reason. That conversion is extraordinarily unlikely. The average proton in the Sun's core waits something like 1 billion years before it happens to undergo that first step. Which is the reason stars last. If either barrier were lower, the Sun would have burned through its hydrogen in a fraction of the time, and there would have been no billions of years of steady warmth for anything slow and complicated to evolve in. Before we follow any star to its end, we need the single fact that governs all of it. A star's entire life, how brightly it shines, how long it lasts, and what it becomes at the end, is determined almost entirely by how much material it had when it formed. Composition matters a little. Rotation and companions matter at the margins. Mass matters overwhelmingly. The reason is that mass sets the weight bearing on the core, which sets the temperature and density required to hold it up, which sets the rate of fusion. And the relationship is steep. A star twice the Sun's mass doesn't shine twice as brightly. It shines roughly 10 times as brightly. 10 times the mass gives thousands of times the luminosity, which means massive stars burn through their fuel at a catastrophic rate despite having more of it. The lifetime falls sharply with mass. Our Sun lasts around 10 billion years. A star 10 times heavier lasts perhaps 20 million, and the very largest last only a few million. At the other end, a star a tenth. The Sun's mass burns so slowly that it can last for trillions of years. So the range of stellar lifetimes spans a factor of about 1 million, and it's set at birth. A star's fate is decided before it ever begins to shine. There's a diagram that organizes all of this, and it's worth a chapter because everything tonight can be located on it. In the early 20th century, two astronomers, Ejnar Hertzsprung in Denmark and Henry Norris Russell in America, independently plotted stars by two properties, their brightness and their color, which corresponds to surface temperature. What emerged was not a random scatter. Most stars fell along a single curving band, running from hot and bright at one end to cool and dim at the other. That band is called the main sequence, and about 90% of stars are on it at any moment. The main sequence is not an evolutionary track. It's the set of stars currently fusing hydrogen in their cores, the long stable phase. Where a star sits along it is determined by its mass. Massive stars at the hot bright end, small ones at the cool dim end. Off the main sequence are other groups. Above and to the right, a scattering of red giants, cool but enormously bright, which means they must be very large. Below and to the left, a faint group of white dwarfs, hot but very dim, which means they must be very small. Those two groups are the subject of tonight. They're what stars become after the main sequence, and their positions on the diagram were a puzzle for decades before anyone understood what they were. Let's start at the small end, with the stars that will outlast everything. A red dwarf is a star of perhaps a tenth to a half the Sun's mass. They're cool, dim and red. Most are far too faint to see with the naked eye, despite being nearby. They're also the overwhelming majority. Roughly 3 out of every 4 stars in our galaxy is one of these, and the proportion may be higher. Our Sun is in the brighter minority. And they last almost unimaginably long. Estimates run from hundreds of billions of years for the larger ones to something like 10 trillion years for the smallest. Two things cause that. First, their cores are cooler and less dense, so fusion proceeds far more slowly. Second, and this is the crucial one, they're fully convective. The whole star churns, so material from the outer layers is continually carried down into the core. A sun-like star can only burn the hydrogen in its central 10% or so, because nothing mixes the outer layers inward. A red dwarf can burn essentially all of its fuel. So no red dwarf that has ever formed anywhere in the universe has had time to die of old age. The universe is 13.8 billion years old, and the shortest lived of them needs 100 billion. Every red dwarf ever born is still burning. Since we can't observe it, everything about red dwarf endings comes from theory. But the theory is fairly clear, and it's a gentle story. As a red dwarf slowly converts its hydrogen to helium, it doesn't swell into a giant the way heavier stars do. The models suggest it contracts slightly and becomes hotter and bluer over hundreds of billions of years, passing through a phase sometimes called a blue dwarf, which has never been observed because none exists yet. Then, as the hydrogen finally runs out, it contracts further and simply fades, becoming a white dwarf made largely of helium, without ever going through a red giant phase or shedding a nebula. There's no explosion, no dramatic ending, no shed shell of glowing gas, just a very long, slow dimming over spans of time that make the current age of the universe look like an opening moment. And because they burn nearly all their fuel, they leave behind less than heavier stars do relative to their size, and they return almost nothing to the galaxy. No enriched material, no elements scattered outward. So the most common ending in the universe, when it eventually starts happening, will be the quietest one, a small red star, growing very slightly bluer for 100 billion years, then dimming out. Nobody will see it. It's simply what the equations say happens if you run them very far forward. There's a category just below stars, and it deserves a chapter because it clarifies what a star is. If a collapsing cloud of gas has less than about 8% of the sun's mass, its core never gets hot enough for sustained hydrogen fusion. It contracts, heats from the compression, glows faintly, and then simply cools. Those objects are called brown dwarfs. They're not planets because they form the way stars do and can briefly fuse deuterium, a heavy form of hydrogen. But they're not stars either because they can't sustain the reaction that defines one. They're dim and cool. Some have surface temperatures comparable to a warm kitchen oven, and the coolest known are around room temperature. They emit almost entirely in the infrared, which is why none was confirmed until 1995, despite being predicted decades earlier. There are a great many of them. Surveys suggest they're roughly as common as stars, possibly more so, though they're difficult to find. And their fate is simply to cool, indefinitely, without any of the drama that awaits their heavier neighbors. They fade from red to infrared to nothing over trillions of years, with no ending event at all. I mention them because they mark the boundary. Below that mass threshold, an object never lights and never has a death to describe, which puts the whole of tonight's subject in perspective. Dying is a privilege of things that burned. Now let's follow a star we know well, because the Sun is the standard case, and its timeline is worth having in order. It formed about 4.5 billion years ago, from a collapsing cloud of gas and dust in a spiral arm, along with the planets. It's been fusing hydrogen in its core ever since, stably. It's roughly halfway through that phase. Around 5 billion years remain before the core hydrogen is exhausted. But it isn't constant. As helium accumulates in the core becomes denser and contracts slightly, which raises the temperature, which speeds up fusion. So the Sun brightens very gradually, about 1% every 100 million years. That's imperceptible on any human scale, but over 1 billion years it adds up. Current models suggest that within roughly 1 billion years, the increased warmth will disrupt the Earth's long-term carbon cycle and eventually drive the oceans into the atmosphere. So the Earth's habitability ends long before the Sun does, a distinction worth keeping straight. The dramatic phases we're about to describe happen to a planet that has already been uninhabitable for billions of years. Let's follow what happens when the hydrogen in the core finally runs out, because the sequence is counterintuitive. You might expect the star to cool and shrink. It does the opposite. When fusion in the core stops, the outward pressure it was providing stops too. So the core contracts under its own weight. And contraction heats things. Gravitational energy becomes thermal energy. That heat doesn't restart core fusion, because the core is now helium, and helium requires far higher temperatures than the core has reached. But it does heat the layer of hydrogen immediately surrounding the core, which is still fuel. And that shell ignites. Hydrogen begins fusing in a thin layer around the inert helium core, at a higher temperature than the core ever had, so it burns faster and produces more energy than before. The result is that the star gets brighter, not dimmer, and the extra energy pushes the outer layers outward. The star begins to swell. That's the transition off the main sequence, and it takes a few 100 million years for a star like the Sun. It's called the subgiant phase, and it's the beginning of the ending. Then comes the phase everybody has heard of, and it's worth taking slowly. As the shell burning intensifies, the star's outer layers expand enormously, by a factor of 100 or more in radius. The Sun will swell out past the orbit of Mercury, past Venus, and possibly to about the Earth's current orbit. And as it expands, the surface cools. Spread the same energy output over a vastly larger surface, and each square meter emits less, so the temperature drops from about 6,000 degrees to perhaps 3,000. Cooler surfaces glow redder, so the star becomes enormous and red, a red giant. Its total luminosity, though, rises dramatically, thousands of times the Sun's current output, because the shell burning is so much more vigorous. It also begins losing mass. The outer layers are so distended that the star's gravity barely holds them, and a strong stellar wind carries material away, potentially a substantial fraction of the star's total mass over this phase. That mass loss matters for the planets, incidentally. As the Sun loses mass, its gravitational hold weakens, and the planets drift outward. Whether the Earth ends up inside the swollen Sun or just outside it depends on a competition between the star expanding and the orbit widening, and current models are genuinely uncertain about the outcome. Either way, it wouldn't be habitable. The surface would be hot enough to melt rock long before the Sun arrived. While the outer layers are swelling, something dramatic is building at the center, and it happens in a matter of seconds after millions of years of preparation. The helium core keeps contracting and heating as the shell above dumps more helium onto it, and it becomes so dense that it enters the degenerate state, where the pressure comes not from heat, but from the quantum rule preventing electrons from occupying the same state. Degenerate matter has a peculiar property. Its pressure doesn't depend much on temperature, which removes the thermostat. In an ordinary gas, adding heat causes expansion, which cools things and regulates the process. In degenerate matter, adding heat doesn't cause expansion. So when the core finally reaches about 100 million degrees and helium fusion ignites, there's nothing to hold it back. The temperature rises, which speeds up the reaction, which raises the temperature further. A runaway. In a few seconds, the core releases energy at a rate comparable to an entire galaxy. It's called the helium flash. And from outside, nothing happens. All of that energy goes into lifting the degeneracy, heating the core until it expands and becomes an ordinary gas again. And it never reaches the surface. The star's appearance changes only slowly over the following thousands of years, as it settles into a new configuration. An enormous event, entirely contained, invisible from outside, which I find rather a wonderful thing about stars. Some of the most violent moments in their lives leave no trace at all on what we see. After the flash, the star settles into a new stable phase, and it's a calmer one. Helium fuses into carbon by a route that took years to work out. Two helium nuclei combine into beryllium-8, which is unstable and falls apart almost instantly in about 10 to the minus 16 seconds. So a third helium nucleus must arrive during that vanishing window. That should essentially never happen. The reason it does is a coincidence in nuclear physics. Carbon has an energy level positioned almost exactly where it needs to be to make the reaction resonant, dramatically boosting the rate. Fred Hoyle predicted that level must exist, in 1953, purely on the grounds that carbon exists, and therefore the reaction must work. Experimentalists looked and found it where he said. It remains one of the most striking predictions in the history of physics. So the star now has two sources, helium fusing in the core and hydrogen fusing in a shell around it. It shrinks somewhat from its red giant size and becomes hotter, occupying a region of the diagram called the horizontal branch. This phase lasts perhaps 100 million years for a star like the Sun, about a tenth as long as the main sequence, because helium burning is less efficient and the star is more luminous. And then the helium in the core runs out too, and the same sequence repeats, one level deeper. With the core helium exhausted, the core contracts again, and now there are two shells burning around it, helium in one, hydrogen in another, further out. The star swells again, larger than before, brighter than before, cooler at the surface than before. It climbs back up the diagram along a track that runs close to the earlier red giant path, which is why this phase is called the asymptotic giant branch. At this stage, the Sun would be at its largest, hundreds of times its current radius, perhaps a few thousand times its current luminosity. And it becomes unstable. The two burning shells don't cooperate well. The helium shell tends to ignite in bursts rather than burning steadily, building up fuel, flashing, dying down, and building up again over thousands of years. Those are called thermal pulses, and each one sends a wave of energy through the star, causing it to expand and contract and driving material off the surface. So the late stages of a Sun-like star are not smooth. They're a series of convulsions, spread over tens or hundreds of thousands of years, each one shedding more of the outer envelope into space. That's how the star gets rid of most of its mass, not in one event, but in pulses, over a comparatively brief final phase. Something important happens during those pulses, and it's the reason we exist. The thermal pulses drive deep convection. The churning reaches down into regions where fusion has been producing carbon and other elements, and carries that material up to the surface. That's called dredge-up, and it happens several times during the giant phases. The result is that the star's outer layers become enriched in carbon, nitrogen, and elements built by a slow process of neutron capture that operates in these stars, barium, strontium, and much of the world's supply of certain heavy elements. And then the stellar wind blows those enriched layers away into space. So Sun-like stars are not just consumers, they're manufacturers, and their late phases are when they deliver. Roughly half of all elements heavier than iron are thought to come from this slow neutron capture process in aging giant stars, and a substantial fraction of the universe's carbon and nitrogen comes from the same source. The carbon in your body, every molecule of it, was made inside a star, and much of it was probably made in a star like this one, in its last few 100,000 years, and then gently blown outward. Not in an explosion, in a wind from a swollen red star, pulsing quietly at the end of its life. Then comes the final act for a star like the Sun, and it's one of the most beautiful things in astronomy. By the end of the pulsing phase, the star has lost a large fraction of its mass, perhaps half or more. What remains is a very hot, very dense core surrounded by a thinning envelope. As the last of the envelope is driven away, the core is exposed, and that core is extraordinarily hot, 100,000 degrees or more at the surface, radiating fiercely in the ultraviolet. That radiation catches up with the gas that was shed earlier, drifting outward at perhaps 10 or 20 kilometers per second. The ultraviolet light ionizes it, and the ionized gas glows. The result is a glowing shell of expanding gas, lit from within by the exposed core, often intricately structured in colors produced by specific elements. Oxygen in green, hydrogen in red, and so on. They're called planetary nebulae, and there are thousands catalogued. They're among the most photographed objects in the sky. And they're brief. A planetary nebula expands and thins and fades within about 10,000 to 20,000 years, an instant by stellar standards. Which is why, despite billions of stars in our galaxy reaching this stage, Only a few thousand nebulae are visible at any one time. The name deserves a chapter, because it's one of astronomy's better mistakes. William Herschel, the astronomer who discovered Uranus and one of the great observers of the 18th century, catalogued a number of small round fuzzy objects that looked through his telescopes like the greenish disks of planets. He called them planetary nebulae, and the term stuck. They have nothing whatever to do with planets. They're shed stellar envelopes, and the resemblance is entirely an artifact of small telescopes and low resolution. A round glowing shell looks like a disk. By the time anyone understood what they actually were, well into the 20th century, the name was too entrenched to change. It appears in every textbook, and astronomers have simply learned to explain it every time. There are periodic suggestions to rename them, and nothing ever comes of it. Scientific terminology survives on inertia rather than accuracy. I quite like that at this hour. One of the most beautiful classes of object in the universe is permanently named after a misunderstanding by a man looking through a homemade telescope in his garden in the 1780s. Let's spend a chapter on what they look like, because the variety is remarkable and partly unexplained. The simplest picture would predict spheres. A star sheds material evenly in all directions, and you get a glowing ball, appearing as a ring because you're looking through more gas at the edges than the center. Some are like that, but many are not. There are hourglass shapes with two lobes extending in opposite directions. There are spirals and multiple nested shells, and structures with jets and knots and delicate filaments. The ring nebula in Lyra, visible in a small telescope, is a classic ring, though detailed imaging shows it's more like a barrel seen end-on. The Cat's Eye Nebula has at least 11 concentric shells, suggesting pulses every 1500 years or so. The Helix Nebula, the nearest bright one, shows thousands of cometary knots pointing away from the central star. Explaining the non-spherical shapes has taken decades, and the leading answer is companions. A binary star, or even a large planet, orbiting inside the expanding envelope would channel the outflow into a disk and drive jets along the poles. That idea has gained ground steadily, and some now argue that most non-spherical planetary nebulae involve a companion of some kind, which means many of these beautiful objects are shaped not by the dying star alone, but by something orbiting it that we can't see. When the nebula has drifted away, what remains is the exposed core, and that object is one of the strangest things in the universe. A white dwarf is roughly the mass of the Sun compressed into a sphere about the size of the Earth. Its density is around 1 million times that of water. A teaspoon would weigh several tons. It has no fuel. Fusion has stopped entirely. It doesn't generate energy. It simply radiates away the heat it already has slowly, over billions of years. For a star like the Sun, the white dwarf would be about half a solar mass, composed mainly of carbon and oxygen, the products of helium fusion, with a thin layer of lighter elements on top. Its surface starts extremely hot, over 100,000 degrees, and cools gradually, to 20,000 degrees over tens of millions of years, to 10,000 over a billion, and downward from there indefinitely. And that's the ending for the great majority of stars. Something like 97% of the stars in our galaxy, including the Sun, will end as white dwarfs, small, dense, cooling remnants, with a beautiful but brief nebula as a farewell. A white dwarf should collapse. It has the mass of a star and no energy source to push back against gravity. So what stops it? The answer is the same quantum rule we've discussed on other nights. The Pauli exclusion principle, which says no two electrons can occupy the same quantum state. Squeeze a collection of electrons into a smaller volume, and they must occupy higher and higher energy states, because the low ones are already full and no two can share. That resistance produces a pressure, and crucially, it doesn't depend on temperature. So a white dwarf is held up by a counting rule about which states are allowed. It can cool to absolute zero and still not collapse, because the support has nothing to do with heat. That property has an odd consequence. White dwarfs get smaller as they get heavier, add mass, and the increased gravity compresses the electrons further and the star shrinks. The relationship runs the opposite way to ordinary objects, which means there's a limit. Push the mass high enough, and the electrons are forced to move at nearly the speed of light, and relativity changes how their pressure scales, and above a certain point, they cannot hold at all. That limit is about 1.4 solar masses, and it's one of the most important numbers in astrophysics. The story of that number is worth a chapter, because it has an unfortunate middle and a satisfying end. In 1930, Subramanian Chandrasekhar was 19, traveling by ship from India to Cambridge to begin his doctorate. During the voyage, he worked out what happens to a white dwarf as you increase its mass, incorporating relativity into the calculation. He found the limit. Above roughly 1.4 solar masses, no stable configuration exists. He presented the result in London in 1935. Arthur Eddington, the most eminent astrophysicist in the world and previously a supporter, stood up immediately afterwards and dismissed it publicly, saying there ought to be a law of nature to prevent a star behaving in such an absurd way. Eddington's authority carried enormous weight, and the result was set aside for years. Chandrasekhar was, by his own account, devastated. He eventually left the topic entirely and moved to the United States, where he had a long and distinguished career in other areas. He was right. The limit is real, it's fundamental, and it determines whether a dying star ends as a white dwarf or as something denser. He received the Nobel Prize in 1983, 53 years after the voyage. There's a NASA X-ray observatory named after him now, which has spent a quarter of a century observing exactly the objects his calculation described. Let's follow a white dwarf forward, because its future is the longest and quietest part of tonight. It has a fixed amount of heat and no way to make more, so it radiates and cools, and the process slows as it goes. A cooler object radiates less, so the cooling decelerates. The sequence runs from white-hot through yellow and orange to red over billions of years. The oldest white dwarfs in our galaxy, formed from the first generation of Sun-like stars, have been cooling for around 12 billion years and are now down to a few thousand degrees. Because the cooling rate is calculable, the coolest white dwarfs act as a clock. Finding the faintest ones in a star cluster and measuring their temperature tells you how long they've been cooling, and therefore the cluster's age. That's one of the independent checks on the age of the universe. Eventually, in theory, a white dwarf cools to the temperature of its surroundings and stops emitting detectably. Such an object is called a black dwarf. None exists. The universe is not old enough. The process takes something like 100 billion years or more, and only 13.8 billion have passed. So the final state of 97% of stars is something that has never yet occurred anywhere in the universe, and won't for a very long time. There's a detail about that cooling that was predicted decades ago and confirmed recently, and it's genuinely lovely. As a white dwarf cools, the carbon and oxygen nuclei inside it, packed at enormous density in a sea of electrons, eventually slow enough for their mutual electrical repulsion to lock them into place. They crystallize. The interior transitions from a dense fluid into a solid lattice, starting at the center and working outward. That was predicted in the 1960s, and the process releases latent heat, exactly as water releases heat when it freezes, which slows the cooling temporarily and causes a pileup of white dwarfs at particular brightnesses. In 2019, analysis of data from the Gaia spacecraft found exactly that pileup, an excess of white dwarfs at the temperatures where crystallization was predicted to occur. It was the first solid observational confirmation. So a substantial fraction of the white dwarfs in our galaxy have solid cores, crystallized carbon and oxygen under enormous pressure. The popular framing calls them diamond stars, which overstates it. The structure isn't diamond, and the material bears little resemblance to a gemstone. But the underlying fact is real and rather beautiful. Stars at the end freeze from the inside out. The discovery of white dwarfs is a good story, and it began with a star behaving oddly. Sirius is the brightest star in our sky. In the 1840s, Friedrich Bessel noticed that its position wobbled slightly over time, following a small elliptical path superimposed on its motion across the sky. He concluded that it must be orbiting something unseen, and calculated the companion's mass and orbit from the wobble alone. It was an early example of finding an invisible object by its gravitational effect. The companion was spotted in 1862 by Alvan Graham Clark, an American telescope maker, while testing a new lens. It was faint, about 10,000 times dimmer than Sirius itself. And then the puzzle. Its mass, from the orbit, was about that of the Sun. But its brightness was tiny. When its temperature was eventually measured and found to be very hot, the only way to reconcile hot, heavy and faint was for it to be extremely small, roughly the size of the Earth. That implied a density nobody could believe. Eddington wrote that the message from the star seemed to be, "I am composed of material 3,000 times denser than anything you have ever come across. A ton of my material would be a little nugget you could put in a matchbox." It took quantum mechanics in the late 1920s to explain how such a thing could exist without collapsing. Now let's turn to the stars that don't end quietly, because above a certain mass, everything changes. For stars above roughly 8 to 10 times the Sun's mass, the story diverges. Their cores get hot enough to keep fusing past helium, and each new stage brings them closer to a limit that white dwarfs never reach. Where a Sun-like star stops at carbon and oxygen, unable to fuse them because its core never gets hot enough, a massive star's core contracts and heats until carbon ignites. And then it keeps going. Carbon fuses to neon and magnesium. Neon fuses to oxygen. Oxygen fuses to silicon and sulfur. Silicon fuses to iron. Each stage requires a higher temperature, releases less energy per reaction, and is dramatically shorter than the one before. For a star of about 20 solar masses, the numbers are extraordinary. Hydrogen burning might take 10 million years, helium 1 million, carbon 1,000, neon a few years, oxygen a few months, and silicon burning takes about a day. Because each stage happens at a different depth, the star develops a layered structure, and it's a striking image. The outermost layers are still hydrogen, unburnt. Below them, a shell where hydrogen is fusing into helium. Below that, a helium layer, with a shell fusing helium into carbon. Then carbon, with its own burning shell. Then neon, then oxygen, then silicon. And at the very center, growing, a core of iron. Each layer is fusing at its own boundary, each shell producing energy, each successive layer denser and hotter than the one above. The whole structure is often described as an onion, and the analogy holds well. The scale is peculiar. The star as a whole might be as large as the orbit of Jupiter, an enormous distended envelope. But the iron core at the center is only about the size of the Earth, containing perhaps 1.5 solar masses. So the interesting part is a tiny fraction of the volume, and the vast bulk of the star is a thin outer envelope that barely knows what's happening below. That's why the final day looks so ordinary from outside. A star can be in its silicon burning phase, hours from catastrophe, and appear from a distance exactly as it did 1,000 years earlier. Iron is the hinge, and it deserves its own chapter. Fusion releases energy because the product is more tightly bound than the ingredients. The resulting nucleus weighs slightly less than the parts, and the difference emerges as energy. But that only works up to a point. If you plot binding energy per particle against atomic mass, it rises steeply for the lightest elements, and then flattens and peaks around iron and nickel, and then declines. Iron sits at the top. It is the most tightly bound nucleus there is, which means there is no energy to be gained by fusing it into anything heavier. So when the core becomes iron, the process that has supported the star for its entire life simply stops working. Fusing iron would consume energy rather than releasing it. The core is then held up only by electron degeneracy pressure, the same support as a white dwarf, and it keeps growing as the silicon shell above continues dumping fresh iron onto it. When it exceeds the Chandrasekhar limit, the same 1.4 solar masses Chandrasekhar calculated on that ship, the electrons cannot hold. After 10 million years of stability, the core has about a quarter of a second left. What happens next is the most violent event in the modern universe, and nearly all of it takes less than a second. The core collapses. A region, roughly the size of the Earth, falls inward to a sphere about 20 kilometers across. Infall speeds reach a substantial fraction of the speed of light, around a quarter of it by the time material arrives at the center. As the density rises, the matter itself transforms. Electrons are squeezed so hard that it becomes energetically favorable for them to merge with protons, converting each pair into a neutron and releasing a neutrino. That process, neutronization, does two things. It removes the electrons, whose pressure was providing support, accelerating the collapse, and it produces an enormous flood of neutrinos. The collapse halts abruptly when the material reaches the density of an atomic nucleus, where neutron degeneracy pressure and the strong nuclear force resist further compression, and the infalling core, arriving at speed, bounces. A shockwave forms and starts moving outward through the star. That's the moment of formation. Somewhere in the middle of a star that has existed for 10 million years, an object 20 kilometers across has just come into being, and it will outlast everything around it. Here's the part that troubled theorists for decades, and it's a good illustration of how hard this problem is. The bounce alone doesn't produce an explosion. The shockwave travels outward, but it loses energy breaking apart the iron nuclei it passes through. Each dissociation consumes energy, and within a few tens of milliseconds, it stalls. For years, simulations of core collapse reliably produced a stalled shock and no explosion. The star would collapse, bounce, and then simply keep collapsing, with the shock sitting motionless while material rained down through it, which is a problem, because supernovae plainly do happen. Something must revive the shock. The leading answer involves the neutrinos. The newly formed neutron star at the center is at hundreds of billions of degrees, and it radiates almost its entire gravitational binding energy as neutrinos over about 10 seconds. Neutrinos barely interact with anything, but there is so much material at such extreme density just above the core that a small fraction of them, perhaps 1%, is absorbed. And that fraction deposits enough energy to reheat the stalled shock and drive it outward. 1% of the neutrino energy suffices to blow apart an entire star, which tells you how enormous the total is. About 99% of a core collapse supernova's energy leaves as neutrinos invisibly, and the spectacular light we see is a fraction of a percent of the whole. The revived shock then works its way outward through the layers of the star, and this part is comparatively slow. It takes hours to cross the enormous distended envelope. The outer layers that are as large as the orbit of Jupiter and barely aware of anything happening below. When the shock finally reaches the surface and breaks out, there's a brief, intense flash of ultraviolet and X-rays, lasting minutes to hours. That's called shock breakout, and it's been caught by accident a handful of times by satellites watching other things. Then the star brightens over days or weeks as the expanding debris, heated by the shock and by the decay of radioactive nickel created in the explosion, radiates. At peak, a core collapse supernova can shine with a few billion times the sun's luminosity, briefly rivaling the combined light of its entire host galaxy. Then it fades over months, following a decline set largely by the radioactive decay of cobalt into iron, a light curve whose shape is a direct fingerprint of the nuclear physics inside. And what's left is an expanding cloud of debris, enriched with newly forged elements, moving outward at thousands of kilometers per second into the surrounding interstellar gas. Let's spend a chapter on the manufacturing, because it's the reason supernovae matter beyond spectacle. During the star's life, fusion built elements up to iron in the successive burning shells. All of those are released in the explosion. But the explosion itself makes more. The shock passing through the layers briefly raises temperatures far above anything the star achieved in ordinary burning, driving rapid fusion, explosive nucleosynthesis, which produces substantial quantities of elements like silicon, sulfur, calcium, and nickel. Radioactive nickel, 56, is produced in large amounts, perhaps a tenth of a solar mass, and its decay through cobalt to iron powers the visible light of the event for months afterwards. There's also a flood of neutrons in the innermost regions, which can drive rapid neutron capture and build elements heavier than iron. How much of the universe's heavy element inventory comes from supernovae versus from neutron star mergers is an active question, with the balance having shifted toward mergers in recent years for the heaviest elements. But the intermediate elements, much of the oxygen, silicon, magnesium, and calcium in the universe, come predominantly from these explosions. Which means the calcium in your bones, and much of the oxygen you're breathing, was made in the last seconds of a massive star and thrown outward across the galaxy long before the Sun existed. Astronomers classify supernovae, and the scheme is historically confusing enough to deserve a chapter. The original division was purely observational, based on spectra. Type 1 supernovae show no hydrogen lines. Type 2 do. That's it. The distinction was made before anyone knew what caused either. Then subdivisions accumulated. Type B shows a strong silicon feature. Type EB shows helium but no silicon. Type EC shows neither. And it turned out the physical grouping cuts across the observational one. Types EB, IC, and 2 are all core collapses of massive stars. The difference is simply how much of the outer envelope the star had lost before exploding. A star that lost its hydrogen shows no hydrogen lines. One that lost its helium too shows neither. Type O is something else entirely, not a core collapse at all, but the detonation of a white dwarf. It shares a category with the others only because of an accident of spectral appearance. So the classification is a fossil of the order in which things were discovered. Everyone knows it's awkward. Nobody has managed to replace it. Which is a recurring theme in this subject. Planetary nebulae aren't planets. Type EA isn't related to IB, and the names persist regardless. Let's follow the other kind of explosion, because it involves an object we've already discussed, and it ends very differently. A white dwarf is stable indefinitely, as long as nothing adds to it. But many stars have companions, and if a white dwarf can pull material from a nearby star, it grows. As it approaches the Chandrasekhar limit, conditions in its interior become extreme, and at some point, before the electrons actually fail, the carbon in the core ignites. Because the material is degenerate, there's no thermostat. Heating doesn't cause expansion, so the reaction runs away, exactly as in the helium flash, but with far more energy available. The result is total. A burning front sweeps through the entire object in a couple of seconds, fusing much of it into heavier elements and releasing enough energy to unbind the star completely. Nothing is left behind. No remnant, no neutron star, no black hole. The white dwarf is entirely destroyed, converted into an expanding cloud of freshly made iron group elements moving at 10,000 kilometers per second. That's a type EA supernova, and it's the main source of iron in the universe. Most of the iron in your blood was made this way, in the detonation of a dead star that had been quietly cooling for billions of years before something tipped it over. There's genuine uncertainty about the trigger, and it's been argued over for decades. The traditional picture is called the single degenerate channel, a white dwarf with an ordinary companion star, pulling material off it steadily, accumulating mass until it reaches the threshold. That has difficulties. Accreting material stably is harder than it sounds. Too fast and it puffs up. Too slow and it detonates in surface flashes without accumulating. And searches for the surviving companion star in nearby remnants have generally come up empty, which is awkward because a companion should survive. The alternative is the double degenerate channel. Two white dwarfs in a binary, spiraling together as gravitational waves drain their orbit, and eventually merging or detonating on contact. That avoids the companion problem because both objects are destroyed, and such binaries are known to exist in the right numbers. There's also a third possibility, in which a surface layer of helium detonates first and drives a shock into the core, triggering the main explosion below the Chandrasekhar mass entirely. The current view is that more than one channel probably operates in different proportions, which is unsatisfying, and it matters, because these explosions are used as cosmic measuring tools, and it will be good to know exactly what they are. That use deserves a chapter, because it led to one of the biggest discoveries in cosmology. Because type Ia explosions occur at a consistent mass threshold, they release a consistent amount of energy and reach a consistent peak brightness. Not identical, but close. And there's a correction that tightens it considerably. The intrinsically brighter ones fade more slowly, in a regular, calibratable way. Measure the shape of the light curve over the weeks after the explosion. Apply the correction, and the scatter drops sharply. That turns them into standard candles. Know the true brightness, measure the apparent brightness, and you have the distance. And because they're so luminous, they're visible across billions of light years. In the 1990s, two competing teams used them to measure how the expansion of the universe had been slowing down. The distant explosions came out fainter than expected, further away than a decelerating universe could put them. The expansion isn't slowing, it's accelerating, driven by something we call dark energy, which makes up about 68% of the universe, and which nobody can identify. So a discovery about the fundamental composition of the cosmos came from measuring the brightness of exploding dead stars. Objects whose trigger mechanism, 3 decades later, is still debated. Let's spend some chapters on the ones people actually witnessed, because the historical records are remarkable. In the spring of 1006, observers across the world recorded a new star in the southern constellation of Lupus. It appears in Chinese, Japanese, Arabic, and European records, and possibly in rock art in North America. By every account, it was extraordinarily bright, the brightest stellar event in recorded history. Some descriptions suggest it was bright enough to read by at night and to cast shadows. An Egyptian astronomer, Ali ibn Ridwan, wrote a detailed account, describing it as 2 to 3 times the size of Venus and about a quarter the brightness of the moon. A Swiss monastery chronicle recorded it too. It remained visible for years, fading gradually. The remnant was identified in the 20th century, an expanding shell of gas about 7,000 light-years away, still visible in X-rays and radio analysis, indicates it was a type Ia, a white dwarf detonation. And no companion star has been found at its center, which is one of the pieces of evidence favoring the double degenerate channel. So a 1,000-year-old observation, recorded independently on 3 continents, is now a data point in an argument about how white dwarfs explode. The best observed supernova in history happened within living memory, and it confirmed the whole theoretical picture. On the 23rd of February 1987, 3 separate detectors, in Japan, the United States and Russia, each recorded a brief burst of neutrinos, about 24 events in total, spread over roughly 13 seconds. A few hours later, astronomers in the southern hemisphere noticed a new bright star in the Large Magellanic Cloud, a satellite galaxy about 160,000 light-years away. The neutrinos arrived first, exactly as predicted. They escape the collapsing core immediately, while the light has to wait hours for the shock to cross the star and break out at the surface. 24 detected particles, from an event that produced something like 10 to the 58th of them, and that handful confirmed everything: the collapse, the neutralization, the 10-second cooling timescale, the energy budget. It became the most intensively studied supernova ever. It was bright enough to see with the naked eye for months, and it's been observed continuously ever since, in every wavelength, as the debris expands and interacts with material the star shed before it died. It remains the only supernova from which neutrinos have been detected, and one of the most important observations in astrophysics. 2 follow-ups to that event are worth a chapter, because both took decades. The first is the rings. Images taken a few years after the explosion revealed 3 glowing rings around the site, 1 inner ring and 2 larger outer ones, forming an hourglass shape. Their material the star shed before exploding, tens of thousands of years earlier, lit up by the ultraviolet flash from the explosion. As the debris expanded, it eventually reached the inner ring and began slamming into it, causing bright knots to appear one by one around its circumference through the 2000s, a slow-motion collision playing out across decades. The second follow-up concerns what was left behind. A core collapse should produce a neutron star. For 30 years, nobody could find it. That absence was troubling. Various explanations were proposed, including that it had collapsed further into a black hole. Then, over the past several years, evidence accumulated. A warm dust blob at the right position, and eventually infrared observations from the James Webb Space Telescope showing emission consistent with ionization from a compact object at the center. So the neutron star appears to be there after all, hidden inside the dust of its own debris. And it took nearly 4 decades to find. Let's follow the debris forward, because supernova remnants have a life of their own. Immediately after the explosion, the ejecta expand freely at thousands of kilometers per second, essentially unimpeded, a phase lasting a few hundred years. Then they've swept up enough surrounding gas to matter, and the expansion begins to be slowed by it. The remnant enters a phase where the shocked material is very hot, millions of degrees, and glows in X-rays. That lasts tens of thousands of years. Then radiative cooling takes over. The shell is cooled enough to radiate efficiently, which drains its energy, and it slows further, forming the delicate filamentary structures seen in the older remnants. The Veil Nebula in Cygnus is a fine example. The remains of an explosion perhaps 10 or 20,000 years ago. Now a vast, intricate lacework of glowing filaments spread across a region 6 times the width of the full moon, visible in a modest telescope with the right filter. Eventually, after perhaps 100,000 years, the remnant merges with the general interstellar medium and ceases to be distinguishable. By then, it has done its job, distributing the star's manufactured elements across hundreds of light years and compressing the surrounding gas, which can trigger the collapse of nearby clouds and the formation of new stars. That last point deserves its own chapter, because it's the reason any of this matters for us. The first stars formed from hydrogen and helium alone, the only elements the early universe made. There was no carbon, no oxygen, no iron, no silicon. Every heavier atom was manufactured inside stars and released when they died, gently in the winds, and shed envelopes of sun-like stars. Violently in supernovae, and in the collisions of the neutron stars that supernovae leave behind. That enriched material mixed into the interstellar gas, and when the next generation of stars formed from that gas, they were slightly richer than their predecessors, and so on, generation after generation, over billions of years. By the time a particular cloud in a spiral arm collapsed 4.5 billion years ago to form the Sun and its planets, that gas had been enriched by many previous generations, enough that there was silicon and iron and oxygen and carbon in quantities sufficient to build rocky worlds, and eventually bodies. So the deaths we've been describing are the reason there is anything except hydrogen and helium. A star's ending is a delivery. And it's still happening. Every supernova in every galaxy tonight is adding to the inventory, and somewhere in our own galaxy, gas enriched by an earlier death is currently collapsing into a new star. Let's look properly at what a core collapse leaves behind, starting with the more common outcome. For progenitor stars of roughly 8 to 20 solar masses, the collapsing core stops at nuclear density and becomes a neutron star, about 1.5 solar masses in a sphere 20 kilometers across. The density is beyond ordinary comparison. A teaspoon would weigh hundreds of millions of tons. The surface gravity is around 200 billion times Earth's. It spins rapidly because the collapsing core conserved its angular momentum while shrinking by a factor of 100,000, the same effect that makes a skater speed up when they pull their arms in. And it has an enormous magnetic field for the same reason. The field lines were compressed along with the material, amplifying the field by a similar factor. Spin plus magnetic field produces beams of radiation from the magnetic poles, sweeping around as the star rotates. If one of those beams happens to cross our line of sight, we see a pulse once per rotation, a pulsar, keeping time with a precision comparable to atomic clocks. Around 3,000 have been catalogued. Our galaxy probably contains 100 million or more, most of them old, cold, beamless, and completely undetectable. There's a curious detail about neutron stars worth a chapter. They're usually moving very fast. Ordinary stars in the galactic disk move at perhaps 20 or 30 kilometers per second relative to their neighbors. Neutron stars average several hundred, and some exceed 1,000, fast enough to escape the galaxy entirely. Something kicks them during formation, and the explanation is asymmetry. If the collapse and explosion were perfectly spherical, momentum would balance and the remnant would stay put. But simulations show the process is turbulent and lopsided. The ejected material and the neutrino emission are both uneven, and even a few percent imbalance imparts a substantial recoil to an object of that mass. There's direct evidence. Some pulsars are found far from the center of their own supernova remnant, with a trail of disturbed gas behind them, moving outward. And the direction and speed can sometimes be traced back to the explosion site. So a neutron star is usually a fugitive, thrown out of its birthplace at hundreds of kilometers per second, on a path that will carry it across the galaxy and never bring it back. Which adds a small poignancy to the picture. The remnant doesn't stay with the remains. It leaves immediately, and the debris disperses behind it. For the heaviest stars, the collapse doesn't stop. If the core exceeds roughly 2 to 2.5 solar masses, neutron degeneracy pressure and the strong force cannot hold it either. There is no known force that can, and nothing in the theory suggests one exists. So the material continues collapsing, past the point where its escape velocity exceeds the speed of light, and an event horizon forms around it. What remains is a black hole, typically 5 to a few tens of solar masses for a stellar remnant. The threshold in terms of the original star is uncertain. Roughly, stars above about 20 to 25 solar masses are thought to produce black holes, but the boundary is not sharp and depends on rotation, composition, and how much mass the star lost during its life. Some black holes form with an explosion. When the shock succeeds initially, a material later falls back onto the remnant. Others may form quietly, with no explosion at all, which brings us to one of the more haunting observations in modern astronomy. Our galaxy is thought to contain something like 100 million stellar black holes, essentially all of them invisible, unless something falls into them or they merge with a companion. Some massive stars appear not to explode at all, and the evidence for it is one of the stranger results in recent astronomy. The idea is called a failed supernova. If the shock never revives, if the neutrinos don't deposit enough energy, then the collapse simply continues. The whole star falls inward, and a black hole forms without any explosion. From outside, the star would brighten slightly and briefly as its outer envelope was disturbed, and then disappear. Since 2008, a survey has monitored around 1 million supergiant stars in nearby galaxies, watching for exactly that, a star that vanishes without exploding. They found a candidate, a star of about 25 solar masses in a galaxy 20 million light-years away. Brightened modestly in 2009, then faded, and by the mid-2010s it was gone from optical images, with only a faint infrared source remaining. The interpretation is contested. Some analyses suggest it may be obscured by dust rather than absent, and follow-up work continues. But the general expectation from theory is that a substantial fraction of massive stars, perhaps 10 to 30%, end this way, collapsing quietly into black holes. Which means some of the stars in the sky tonight will not explode. They will simply stop, and something dark will be there instead, and nobody watching from a distance would see much at all. Let's lay out the mass ranges, with appropriate caveats, because it's satisfying to have the map in one place. Below about 8% of a solar mass, never a star. A brown dwarf, cooling forever. From there up to about half a solar mass, a red dwarf, burning for hundreds of billions to trillions of years, ending as a helium white dwarf without a giant phase. From about half to 8 solar masses, the Sun's path. Red giant, helium burning, second giant phase with thermal pulses, planetary nebula, and a carbon-oxygen white dwarf. From about 8 to 10 solar masses, a transitional region, poorly understood, where stars may produce oxygen neon white dwarfs, or may undergo an unusual kind of collapse triggered by electrons being captured onto nuclei. From about 10 to 20 solar masses, core collapse, supernova, neutron star. Above about 20 or 25, core collapse producing a black hole, sometimes with an explosion, sometimes quietly. And every one of those boundaries is uncertain by a solar mass or two, and depends on composition, rotation, and whether the star had a companion. They're not sharp lines, but blurred transitions, and the details are still being worked out. That map assumes stars live alone, and most massive stars don't, which changes everything. Surveys suggest that the majority of massive stars, perhaps 70% or more, have a close companion, and that most of those will interact, exchanging mass, merging, or stripping each other. Mass transfer changes a star's fate directly. A star that loses its hydrogen envelope to a companion explodes as a different type, leaves a different remnant, and may follow a completely different evolutionary path than it would have alone. There's also common envelope evolution, where one star swells so much that it engulfs its companion, and the two spiral together inside a shared envelope, ejecting it and ending up in a much tighter orbit. That process is thought to produce many of the compact binaries we observe, including the neutron star pairs that eventually merge. And stars can merge outright, producing an object with a mass and composition that no single star would have. So the neat mass-to-fate mapping is a first approximation for isolated stars, and the majority of massive stars aren't isolated, which is one of the main reasons this field remains active. The simple picture was worked out decades ago. The complications, which dominate for the most massive stars, are still being sorted out. Let's spend a chapter at the extreme end, because the biggest stars behave in ways the ordinary picture doesn't cover. The most massive stars known are perhaps 100 to 200 times the Sun's mass. They're extraordinarily luminous, millions of times the Sun, and they live only a few million years. At those luminosities, the radiation pressure pushing outward through the star's own outer layers is close to what gravity can withstand, which makes them unstable. They shed mass continuously in powerful winds, and sometimes in violent eruptions. Some are classified as luminous blue variables, objects that vary erratically in brightness and occasionally undergo enormous outbursts. Eta Carinae is the famous example. In the 1840s, it brightened dramatically, briefly becoming the second brightest star in the sky, and ejected something like 10 solar masses of material in an event now called the Great Eruption. It survived, and the ejected material forms an hourglass-shaped nebula that's still expanding. Nobody fully understands what happened. It wasn't a supernova. The star is still there. It was some kind of enormous instability, and similar events have been observed in other galaxies. Eta Carinae will eventually explode properly. When it does, it will be spectacular, and it's close enough, around 7,500 light-years, to be a notable event without being dangerous. There's a related class worth a chapter, because they're what massive stars become after losing their envelopes. Wolf-Rayet stars are extremely hot, extremely luminous objects with powerful winds, losing mass at rates that would consume a solar mass in 100,000 years. They show strong emission lines of helium, carbon, nitrogen or oxygen, and little or no hydrogen, which means we're seeing material that was in the interior of the star. The outer hydrogen envelope has been stripped away, either by the star's own wind or by a companion, exposing layers that were once deep inside. They're rare, a few hundred known in our galaxy, because the phase is brief, lasting perhaps a few 100,000 years at the end of a massive star's life. And they're the immediate progenitors of certain supernova types. A star that has lost its hydrogen explodes as a type Ib, One that has also lost its helium explodes as a type IC. Some produce spectacular structures. Binary Wolf-Rayet systems can generate spiral plumes of dust, wound outward, like the pattern from a rotating sprinkler, as the winds from two stars collide and the collision point orbits. One such system was imaged recently by an infrared telescope, showing more than a dozen nested dust shells, each produced by a close passage of the two stars, spaced 8 years apart, extending outward for decades of expansion. There's one more kind of ending, and it only happens to a narrow range of very massive stars. If a star's core reaches an enormous mass, roughly 60 to 130 solar masses, something unusual occurs. The core becomes so hot that its photons carry enough energy to spontaneously convert into pairs of particles, an electron and its antimatter counterpart. That conversion removes photons, and photon pressure was part of what held the star up. So the support falters, the core contracts suddenly, the temperature spikes, and oxygen-silicon fuse explosively all at once. The entire star detonates. Not a collapse leaving a remnant, a complete disruption, with nothing left behind at all. No neutron star, no black hole. That's a pair instability supernova, and it releases far more energy than an ordinary core collapse. Such stars are essentially non-existent today, because modern stars lose too much mass through their winds to reach the required core size. But the first generation of stars, formed from pure hydrogen and helium with no heavy elements, had much weaker winds, and may have been massive enough. So this may have been a common ending in the first 100 million years of the universe, and essentially never since. A handful of candidate events have been reported in distant galaxies. None is confirmed beyond doubt, and finding a clear example remains an open goal. Since the 1990s, surveys have found explosions that don't fit the standard categories, and they deserve a chapter. Superluminous supernovae are 10 to 100 times brighter than ordinary ones, and they stay bright far longer. The energy budget is difficult to explain with ordinary radioactive decay. There simply isn't enough nickel produced. Several explanations compete. One is that a rapidly spinning, extremely magnetized neutron star, a magnetar, forms in the collapse, and its spin-down energy is deposited into the expanding debris, keeping it luminous for months. Another is interaction. If the star shed a substantial amount of material shortly before exploding, the debris slams into that shell, converting kinetic energy into light very efficiently. And a third possibility, for the most extreme cases, is the pair instability mechanism we just discussed. They're rare, perhaps 1 in 1,000 supernovae, and they've only been found because modern surveys photograph the whole sky repeatedly and catch things that older, targeted surveys missed. Which is a general pattern in this field. Every time the observational method changes, a new category of stellar death appears that nobody had predicted. There's a phenomenon at the extreme end of stellar death that was discovered by accident, in a rather remarkable way. In the late 1960s, satellites were monitoring the sky for gamma rays, watching for signs of nuclear weapons testing in violation of a treaty. They detected flashes, but from space, not from Earth, and from random directions. The results were declassified and published in 1973, and gamma-ray bursts became one of the great puzzles of astronomy for the following 25 years. Nobody could tell how far away they were, and therefore how energetic. The answer came in the 1990s, when their positions could finally be pinned down quickly enough for other telescopes to find fading afterglows. They were in distant galaxies, billions of light years away, which meant they were the most energetic explosions known. The longer ones, lasting seconds to minutes, are now associated with the collapse of certain rapidly rotating massive stars. Instead of a straightforward explosion, the core forms a black hole surrounded by a disk of infalling material, which drives narrow jets outward at nearly the speed of light. If one of those jets happens to point at us, we see an extraordinarily bright flash, because the energy is concentrated into a narrow cone rather than radiated in all directions. That's a collapsar, and it's the most violent thing a single star can do. There's a second category of gamma-ray burst, lasting less than about 2 seconds, and its origin was confirmed spectacularly in 2017. The suspicion had been that short bursts come from merging neutron stars, two remnants of earlier deaths, spiraling together over billions of years as gravitational waves drain their orbit. On the 17th of August, 2017, gravitational wave detectors registered a signal from two merging neutron stars 130 million light-years away. Less than 2 seconds later, orbiting telescopes detected a short gamma-ray burst from the same direction. Within 11 hours, optical telescopes had located the source. Around 70 observatories on every continent, and in orbit, observed it over the following weeks. The glow that followed, a kilonova, brightened and reddened in a very particular way, matching predictions for the radioactive decay of freshly created heavy elements, which answered a long-standing question. The rapid neutron capture process that makes gold, platinum and uranium requires an enormous flood of neutrons in a fraction of a second, and supernovae had struggled to provide enough. Neutron star mergers do. The estimated yield from that single event was several Earth masses of gold. Let's follow that through, because it connects tonight's subject to something you could hold. Elements up to iron are made by fusion in stars. Beyond iron, fusion costs energy rather than releasing it, so heavier elements require a different process, neutron capture. There are two versions. A slow process, operating over thousands of years inside aging giant stars, produces about half the heavy elements, barium, strontium, lead and others. A rapid process, requiring a flood of neutrons in under a second, produces the rest, including most of the gold and all of the uranium and thorium. That rapid process appears to occur predominantly in neutron star mergers, with some contribution from rare kinds of supernova. So the sequence for a gold atom is: a massive star lives and dies, leaving a neutron star. Another does the same. The two orbit for billions of years, spiraling closer. They merge, and in the fraction of a second when neutron-rich material is flung outward and decompresses, the gold is made. Then it drifts through the galaxy for billions of years, mixes into a molecular cloud, and is gathered into a forming planetary system. Which means any gold in the room came from the deaths of two stars, followed by the death of the two remnants they left behind. It's the end product of four endings. Not every stellar explosion is fatal, and there's a class worth a chapter because it repeats. A nova occurs when a white dwarf accretes hydrogen from a companion. The material accumulates on the surface, compressed by that enormous gravity, into a thin, dense layer. When the layer reaches a critical thickness, after years or decades, the base becomes hot and dense enough to fuse all at once. The result is a thermonuclear flash across the surface, brightening the system by a factor of tens of thousands. The word nova means new, because to earlier observers, a star appeared where none had been visible. Crucially, the white dwarf survives. The surface layer is blown off, and the process begins again. Some systems have been observed erupting repeatedly, at intervals from a year to decades. Several novae occur in our galaxy each year, and a handful become bright enough to see without a telescope. They're much less energetic than supernovae, by a factor of tens of thousands, and they don't destroy anything. The star simply clears its surface and starts accumulating again. Which makes them, in the context of tonight, an exception. An explosion that is not a death, on an object that has already died once. Let's put some numbers on the frequency, because it's more often than people assume. In our galaxy, the estimated core collapse supernova rate is roughly 1 or 2 per century, with type Ia explosions adding perhaps one every few centuries. We haven't observed one with the naked eye since 1604, which is considerably longer than that average. The explanation is dust. Most of the galaxy's massive stars lie in the disk, where our view is obscured, so a substantial fraction of explosions are hidden from optical view. Neutrino detectors would catch a galactic supernova regardless of dust. Several large detectors now operate continuously, linked in an early warning network, ready to alert astronomers within minutes if a burst arrives. Across the whole observable universe, the rate is enormous. Something like 100,000 supernovae explode every hour somewhere. Meanwhile, the quieter deaths are more common still. Sun-like stars ending as white dwarfs, red dwarfs fading imperceptibly. Those outnumber the explosive endings by a wide margin, and they happen continuously and silently. So at any given moment, across the universe, stars are ending at a rate that would be impossible to follow. Almost all of it invisible, almost all of it quiet, and a small dramatic fraction of it lighting up galaxies. There's one nearby candidate everyone asks about, so let's spend a chapter on it. Betelgeuse is the bright reddish star marking one shoulder of Orion. It's a red supergiant, an enormously swollen star that, if placed where the Sun is, would extend past the orbit of Mars. Its mass is estimated at somewhere between 15 and 20 times the Sun's, and its age at around 10 million years, which means it's near the end. It will explode. When it does, it will briefly be as bright as the full moon concentrated into a point, visible in daylight for weeks and casting shadows at night. When is genuinely uncertain. Estimates range from 100,000 years to a few million, with recent analyses proposing various positions in its burning sequence. It could also, in principle, have already happened. Its light takes roughly 500 to 600 years to reach us, so an explosion 500 years ago would still be on its way. And it's safe. The estimated threshold for a supernova to damage Earth's atmosphere is somewhere around 30 light-years. Betelgeuse is well over 400, so it would be the most spectacular astronomical event in recorded history, and entirely harmless, which is a rare combination. There was an episode a few years ago that made people wonder, and the resolution is a nice piece of detective work. In late 2019 and early 2020, Betelgeuse faded dramatically, dropping to about a third of its usual brightness, enough to visibly change the appearance of Orion to the naked eye. It was the faintest it had been in the century of careful records. Speculation followed immediately. Was it about to explode? Observations were mobilized. Imaging showed the star's disk, one of the few stars close enough and large enough to resolve, appearing distinctly non-uniform, with a darkened southern region. The eventual explanation, supported by several independent lines of evidence, was dust. The star ejected a substantial cloud of material, which cooled and condensed into dust grains as it moved away, and that dust blocked a large fraction of the light from part of the surface. A local drop in surface temperature caused by convection appears to have contributed. By spring 2020, it had recovered, and it has behaved normally since, apart from some changes in its pulsation period that are still being studied. So the answer was not an explosion, but a star coughing, throwing off a cloud of material that briefly got in the way of its own light. Let's address the safety question properly, and then set it aside. The usual estimate for a dangerous supernova is somewhere within about 30 light-years, though figures between 20 and 50 appear in the literature depending on the assumptions. The threat isn't heat or blast. At those distances, the danger is high-energy radiation, gamma rays and cosmic rays, which would deplete the ozone layer, allowing more ultraviolet through to the surface for a period of years. Are there candidates that close? No. The nearest star likely to explode is well over 100 light-years away, and the well-known candidates, Betelgeuse, Antares, Spica, are all hundreds of light-years distant. There's also a candidate, white dwarf system, somewhat closer that could in principle produce a type Ia, but the timescale is thought to be enormous and the distance still sufficient. So there is no known threat, and the survey data covering nearby stellar motions is now extensive enough that a surprise is very unlikely. What we do have is evidence of past events, which is more interesting than the risk, and rather remarkable, because it's written into the seafloor. Here's a piece of evidence I find quietly astonishing. There's an isotope, iron-60, that is produced in supernovae, and has a half-life of about 2.6 million years. That's long enough to survive a journey through interstellar space, and short enough that any present on Earth from its formation would have decayed away entirely. So if you find iron-60 in old material on Earth, it must have arrived recently, within the last few million years, from outside. And it has been found in deep-sea sediments and in the manganese crusts that accumulate slowly on the ocean floor, and in lunar samples, and in Antarctic snow. The concentrations peak at layers corresponding to roughly 2 to 3 million years ago, with a second possible peak further back. The interpretation is that one or more supernovae exploded within perhaps 100 to 300 light years of us during that period, and the debris, spreading through interstellar space over hundreds of thousands of years, eventually reached the solar system and settled onto planetary surfaces. Far enough away to be harmless, close enough to leave a residue. So there is a physical record, in rock at the bottom of the ocean, of stars that died while our early ancestors were walking around in Africa. A short reassuring chapter, because the question comes up. Our sun will never become a supernova. It doesn't have anything like the required mass. The threshold is around 8 to 10 solar masses, and the sun is one. Its core will never get hot enough to fuse carbon. It will burn hydrogen, then helium, and then stop, because the electron degeneracy pressure in its core will hold the remaining carbon and oxygen against further contraction, and no further ignition occurs. It also can't become a type Ia, because that requires a white dwarf accreting from a companion, and the sun has no companion. So the sun's ending is settled. Red giant phases, mass loss, a planetary nebula, and a white dwarf of about half a solar mass, cooling for a very long time. No explosion, no neutron star, no black hole. Nothing dramatic beyond a period of swelling that unfolds over hundreds of millions of years. And all of it more than 5 billion years away, well after the Earth has ceased to be habitable for reasons that have nothing to do with the sun's death, and everything to do with its slow brightening. Since our own galaxy has been quiet since 1604, essentially everything we know observationally comes from other galaxies. The technique is simple in principle. Photograph a large patch of sky repeatedly, compare each image to the previous one, and look for points of light that weren't there before. For decades that was done by amateurs, and amateurs still find them. A retired Australian named Robert Evans discovered dozens visually, memorizing the star fields of hundreds of galaxies and noticing when something was out of place, which is an extraordinary feat of visual memory. Modern surveys automate it. A wide-field camera photographs enormous areas of sky every night. Software subtracts the previous image, and candidates are flagged within minutes. One such survey in California has been finding thousands of supernovae per year, and a new observatory in Chile, with the largest astronomical camera ever built, will survey the entire southern sky every few nights, and is expected to find hundreds of thousands. That changes the subject from studying individual events to studying populations, how the types are distributed, how they depend on the host galaxy, how the rare classes fit in. Which is how the unexpected categories keep appearing, not from looking harder at known objects, but from looking at everything repeatedly and noticing what doesn't fit. There's a network waiting for the next one in our own galaxy, and it's a nice piece of international cooperation. When a massive star's core collapses, neutrinos escape immediately and arrive hours before the light, which gives a window. If you detect the neutrinos, you can tell telescopes where to look before the star brightens. So the world's large neutrino detectors in Japan, Italy, Canada, Antarctica and elsewhere are linked in an alert system. If several detect a coincident burst, an automatic alert goes out. That would be the first warning of a galactic supernova, and it would let astronomers catch the shock breakout, the brief initial flash, which has only ever been observed by accident and which carries information about the star's structure at the moment of death. The system has been running for over 2 decades and has never triggered on a real event, which is exactly what you'd expect given a rate of 1 or 2 per century. There are also gravitational wave detectors watching. A core collapse should produce a burst of gravitational waves from the asymmetric motion of the collapsing core, detectable probably only for an event in our own galaxy or very nearby. If a galactic supernova occurs, we would have neutrinos, gravitational waves, and light from the same event, and it would probably settle several open questions at once. It could happen tonight, or in 200 years. There's no way to know, and everything is ready either way. Let's spend a chapter on the theory side, because simulating a supernova is one of the most demanding computations attempted. You need three-dimensional hydrodynamics at extreme densities, with general relativity rather than Newtonian gravity, coupled to the transport of neutrinos of several flavors across enormously varying opacities, with a nuclear equation of state, magnetic fields and turbulence, all at once, with the decisive physics happening in the innermost 100 kilometers over a fraction of a second. For decades, simulations were forced to assume spherical symmetry, and those reliably failed to explode. The shock stalled, and nothing revived it. Adding a second dimension helped, because it allowed convection and turbulence behind the shock, which increases how long material spends in the heating region. Some models then exploded. Three-dimensional models with detailed neutrino transport became feasible only in the last decade or so on some of the largest computers in existence, with single runs consuming millions of processor hours. They explode, often but not always, and with a sensitivity to the progenitor's structure that nobody is entirely comfortable with. So the mechanism that makes neutron stars and black holes is understood in outline and not in detail, 90 years after Badi and Zwicky first proposed the connection. Not for lack of effort. The problem simply couples half of physics together in a small region for a fraction of a second. There's an observational technique that lets us check the whole theory of stellar evolution, and it's elegant. All the stars in a cluster formed at roughly the same time from the same cloud. So they differ mainly in mass, and mass determines how fast a star burns. Plot the cluster's stars by brightness and color, and you get a main sequence with a bend in it. The most massive stars have already exhausted their core hydrogen and moved off toward the giant branch. The less massive ones are still burning. The position of that bend, the turn-off point, is a clock. The longer the cluster has existed, the further down the main sequence the turn-off has crept, because progressively smaller stars have had time to finish. So you can date a cluster by looking at which stars have left. Young clusters have turn-offs high up, with massive blue stars still present. The oldest globular clusters have turn-offs low down, with everything above about the Sun's mass long gone. The oldest give ages around 12 to 13 billion years, consistent with and slightly less than the age of the universe, which is a satisfying check. And every one of those clusters is a snapshot of the theory working. The stars above the turn-off have died, the ones below haven't, and the boundary sits exactly where the models say it should, a chapter on where the numbers in tonight's script come from, because it's not observation alone. Stellar evolution codes are computer programs that model a star as a series of nested shells, each with its own temperature, density and composition, and step the whole thing forward in time. At each step, the code solves the equations of hydrostatic balance, energy generation from the relevant nuclear reactions, energy transport by radiation and convection, and the resulting changes in composition. The inputs come from laboratory physics, reaction rates measured in accelerators, opacities calculated from atomic physics, equations of state for matter at high density. Run a model forward and you get a track, a path through the brightness and color diagram, with timescales for each phase. Run it for many masses and compositions, and you get a family of tracks that can be compared against real clusters. And the agreement is good. The turn-off points, the positions of the giant branches, the relative numbers of stars in each phase, all match within the uncertainties across a wide range of cluster ages. Which is why the timeline for the Sun's future is stated with some confidence, despite being 5 billion years away. It's not extrapolation from a hunch. It's a well-tested calculation, checked against millions of stars currently in every phase we've described. That's worth its own chapter, because it changes how the whole subject feels. We can't watch a single star evolve. The timescales are millions to billions of years, and a human lifetime captures a frozen instant. But we don't have to. The galaxy contains hundreds of billions of stars of every mass and every age, which means every phase we've described tonight is occurring somewhere right now, in large numbers, available to be photographed. Stars on the main sequence, most of what you see. Stars leaving it, the subgiants. Red giants, plenty, including some of the brightest stars in the sky. Helium-burning stars on the horizontal branch, visible in globular clusters. Thermally pulsing giants, catalogued in the thousands. Planetary nebulae, a few thousand known, at every stage from freshly ejected to nearly dissipated. White dwarfs, billions in the galaxy, hundreds of thousands catalogued, at every temperature from 100,000 degrees down to a few thousand. Supernova remnants, hundreds known in our galaxy alone, at every age from 300 years to 100,000. So the film of a star's life exists, not as a continuous sequence, but as an enormous collection of individual frames, which can be ordered by theory into a coherent story. That's how all of this was worked out, not by watching, but by sorting. Let's go back to the beginning for a chapter, because the earliest deaths were different. The first stars formed from hydrogen and helium alone, with no heavier elements, and that changes things substantially. Without heavy elements, gas cools inefficiently. The coolants that let modern clouds fragment into small pieces weren't there, so the first stars are thought to have been considerably more massive than typical stars today. They also had much weaker winds. Stellar winds are driven partly by radiation pushing on heavy elements in the outer layers, and with no heavy elements, that mechanism barely works. So the first stars retain their mass rather than shedding it, which means their deaths were different. Some may have been massive enough for pair instability explosions, which destroy the star completely. Others may have collapsed directly into black holes without exploding, and whatever they produced was the first enrichment, the first carbon, oxygen, and iron in a universe that had none. We've never seen one of these stars, but we may be seeing their chemistry, ancient, extremely metal-poor stars in our galaxy's halo, formed from gas polluted by only one or a few of those first supernovae, still burning today. Their compositions are compared against models of different first star masses and explosion types, and the results generally favor first stars in the tens of solar masses rather than the hundreds. That technique deserves a chapter, because it's a lovely piece of detective work. It's called stellar archaeology. The idea is that some second-generation stars were small enough to survive to the present. Anything under about 80% of the Sun's mass would still be burning after 13 billion years. Such stars are chemical records. Their surface composition preserves the chemistry of the gas they form from, which means they carry a snapshot of what the very first supernovae produced. So astronomers hunt for them, searching survey data for stars with extraordinarily low iron content. Hundreds have been found, some with iron abundances less than a millionth of the Sun's. One, found in a survey using a telescope in Australia, shows no detectable iron at all, only an upper limit, while showing plenty of carbon. That pattern matches models for a first-generation star of perhaps 60 solar masses, exploding relatively feebly, with most of its iron falling back onto the remnant, while lighter material escaped. These stars are all around us, mostly in the galactic halo, distinguishable by their motion as well as their chemistry. Some are bright enough for a small telescope. They've been shining since before our galaxy took its current form, and their surfaces still carry the fingerprints of stars that died in the first 100 million years. Let's count what's out there, because the accumulated remains are substantial. Our galaxy contains perhaps 100 billion to a trillion white dwarfs, the accumulated remnants of every sun-like star that has finished, over 12 billion years. They're a significant fraction of the galaxy's stellar population, by number, though faint enough that most are undetectable. There are perhaps 100 million to a billion neutron stars, of which around 3,000 have been detected as pulsars. The rest are old, cold, beamless, and invisible. And perhaps 100 million stellar mass black holes, essentially all of them undetectable unless something falls in or they merge. So a substantial fraction of the material that has ever been in stars is now locked in remnants, permanently removed from circulation, unavailable for making new stars. That's why galaxies run out. Each generation locks some material away forever, and the recycling is imperfect. Our galaxy forms 1 or 2 stars a year now, down from a rate many times higher when it was young. Eventually, the gas will run too low, and star formation will stop, somewhere around 100 trillion years from now, across the universe as a whole. After which, everything that remains is remnants, cooling in the dark. Let's follow that forward, gently, because it's the final chapter of tonight's subject. The big bright stars are the shortest lived, so they go first. Sun-like stars last 10 billion years, and the red dwarfs, the most numerous by far, last hundreds of billions to trillions. So the last stars burning will be small red ones, and they'll be burning long after everything else has stopped. Somewhere around 100 trillion years from now, the last new star will form, and it will most likely be a red dwarf with trillions of years of fuel ahead of it. Which means the last star to form will also be roughly the last star to die, outliving every other shining thing in the universe by an enormous margin, alone in a dark galaxy of cinders. And then it fades, from red into infrared into nothing, and the era of starlight is over. What remains is white dwarfs cooling towards black, neutron stars cooling in the dark, black holes absorbing whatever drifts near, and cold planets orbiting dead suns. There's no drama in it. The last light in the universe goes out quietly, from a small red star, an unimaginably long time from now, with nobody there to note it. Let's be honest about the gaps, because several are substantial. We don't fully understand the explosion mechanism. Three-dimensional simulations now explode reasonably often but not reliably, and the sensitivity to details is uncomfortable. We don't know precisely which stars produce neutron stars and which produce black holes. The boundary is blurred, depends on rotation and mass loss, and may not be monotonic. Some heavier stars may explode, while some lighter ones collapse quietly. We don't know what fraction of massive stars fail to explode at all, though estimates suggest it's significant. We don't know which channel produces type Ia supernovae, and it's plausibly more than one. We don't fully understand the late stages of massive stars, the instabilities, the eruptions, the mass loss, which determine what the star looks like when it dies. And we don't know exactly how the heaviest elements are apportioned between supernovae and neutron star mergers. What we do know is solid: the mass-lifetime relationship, the burning sequence, the role of degeneracy pressure, the mass limits, and the overall map of which stars become what. The framework is well tested. It's the mechanisms inside it that are still being worked out. The instruments arriving over the next decade or two are aimed squarely at those gaps. The new observatory in Chile will photograph the entire southern sky every few nights for 10 years, finding hundreds of thousands of supernovae, including many caught within hours of the explosion, which is when the most informative early light arrives. Space telescopes observing in the infrared can see through the dust that hides many events, and will find explosions in obscured regions that optical surveys miss entirely. Gravitational wave detectors are being upgraded, and next-generation facilities are being designed that would detect neutron star mergers throughout most of the observable universe, turning a handful of events into thousands per year. Neutrino detectors continue to grow, and the next galactic supernova would produce not 24 events, but tens of thousands, mapping the collapse second by second. And larger telescopes will resolve individual stars in nearby galaxies well enough to identify supernova progenitors directly, comparing images taken before and after to see exactly which star exploded. That last technique has already worked a handful of times, and each success ties an observed explosion to a specific star of known mass and type. Doing it routinely would settle a great deal. That progenitor work deserves a chapter, because it's a satisfying kind of detective story. When a supernova appears in a nearby galaxy, Astronomers go back through archival images of the same position, sometimes decades of them, looking for the star that was there before. Most of the time, nothing is visible. The galaxy is too distant to resolve individual stars. But occasionally, the alignment and the depth are right, and a star can be identified. Then its brightness and color give an estimate of its mass and type, and the resulting explosion can be matched to it. The best-known case is a supernova in the Whirlpool galaxy, where the progenitor was identified in earlier images as a red supergiant of around 20 solar masses. Others have been found since. And the pattern that has emerged is interesting. The identified progenitors of ordinary core-collapsed supernovae are all red supergiants below about 18 solar masses. The more massive ones haven't been caught. That may mean the heavier stars collapse quietly into black holes without exploding, which would fit the failed supernova picture. Or it may reflect the difficulty of the observations. It's called the red supergiant problem, and it's one of the sharper open questions in the field. And it exists entirely because people kept old images and thought to look. A chapter on motivation, because the field is large and it's worth saying why. The immediate reason is that stellar deaths determine the chemical composition of the universe. Every element heavier than helium came from a star's life or death, and understanding the yields, how much of what comes from which kind of star, is necessary to explain the composition of everything, including us. The second reason is that they're the origin of the compact objects, neutron stars and black holes, which are the laboratories for extreme physics that we've discussed on other nights. The third is that type Ia explosions are the measuring sticks that reveal dark energy, and improving them requires understanding what they are. And the fourth is that supernovae shape galaxies. The energy they inject heats, gas, drives winds, and regulates how quickly a galaxy can form new stars. Simulations of galaxy formation without that feedback produce galaxies far too massive. So stellar death sits at the center of several fields at once: nuclear physics, cosmology, galaxy evolution, and the origin of the elements. Which is why it attracts the effort it does, and why the unresolved mechanism at the heart of it, how a stalled shock becomes an explosion, remains one of the more consequential open problems in astrophysics. Let's take stock, gently, before we start winding down. The framework is well established, and it's beautiful in its simplicity. A star's mass at birth determines almost everything about its life and its ending. Below 8% of a solar mass, it never ignites. Up to about half, it burns for hundreds of billions of years and fades quietly. Up to about 8, it swells into a giant, sheds a glowing nebula, and leaves a white dwarf. Above that, it builds an onion of burning shells, makes an iron core, and collapses in a quarter of a second, leaving a neutron star or a black hole, or in rare cases, nothing at all. That map is supported by an enormous body of evidence: cluster turn-off points, the observed populations in every phase, the light curves and spectra of thousands of supernovae, the neutrino burst of 1987, and simulations that reproduce the observations. And within it, the mechanisms remain partly open. Why some stars explode and others don't? What triggers a white dwarf detonation? How much of the heaviest elements come from where? How the stalled shock is revived in detail. So the honest answer to tonight's question is, we know what stars become, with confidence, across the whole mass range. And we're still working out exactly how some of the transitions happen. Which is a good position to be in. The map is drawn, the terrain is being surveyed. Everything we've said about what happens inside a star raises an obvious question. How could anyone possibly check? There are two answers, and both are ingenious. The first is neutrinos. Fusion in the sun's core produces them in vast numbers, and because they barely interact with anything, they escape directly from the center and reach us in 8 minutes, carrying information from the core itself rather than from the surface. Detecting them is extraordinarily difficult, but it's been done since the 1960s in tanks of fluid buried deep underground. And that produced one of the great puzzles of 20th century physics. the detectors found only about a third as many as predicted. For 30 years, that discrepancy sat unresolved. Either the model of the Sun was wrong, or something happened to the neutrinos on the way. It was the neutrinos. They change type as they travel, a process that requires them to have mass, which the standard theory of particles had assumed they didn't. The detectors were only sensitive to one type, and by the time the neutrinos arrived, 2/3 had become something else. So the solar model was right all along, and the anomaly turned out to be a discovery about particle physics rather than about the Sun. The second method is even more surprising. You can hear inside a star. The Sun's surface oscillates. Convection below drives sound waves that travel through the interior, bounce off the underside of the surface, and travel back down, resonating like sound in an organ pipe. The result is that the surface rises and falls by tens of meters in millions of overlapping modes, with periods of around 5 minutes. Each mode penetrates to a different depth, and its frequency depends on the conditions along its path, the temperature, density, and composition it passed through. So by measuring the surface motions extremely precisely and decomposing them into their modes, the interior structure can be mapped. It's the same principle a geologist uses to map the Earth's interior from earthquake waves. That field is called helioseismology, and it has confirmed the solar model in detail. The depth of the convection zone, the internal rotation, the sound speed profile, to remarkable precision. The same technique now works on other stars, using space telescopes that measure tiny brightness variations. It's called astroseismology, and it has given accurate masses, radii, and ages for thousands of stars, including many red giants, whose interiors can be probed to distinguish those burning hydrogen in a shell from those burning helium in the core. Which means the picture of stellar interiors isn't only theoretical. It's been measured from outside by listening. Here's something that was predicted for decades and finally observed in 2023. When a star swells into a red giant, any close orbiting planet is engulfed. That's expected to be a common fate. Most known planetary systems have worlds closer to their star than the eventual giant radius. What happens is that the planet spirals in through the star's outer envelope, is torn apart, and its material is deposited. The star brightens briefly as the energy is released, and dust forms in the ejected material. In 2023, astronomers reported exactly that. An outburst in our own galaxy lasting about 10 days, with an infrared excess afterwards indicating dust, matching predictions for a planet of roughly Jupiter's mass being swallowed by an aging star. It's the first direct observation of the process, and it's the fate that awaits Mercury and Venus, and possibly the Earth, in about 5 billion years. There's also indirect evidence in some stars, whose compositions suggest they've absorbed planetary material, showing enrichment in elements that would come from rocky bodies. So the swelling we described in the earlier chapters isn't purely theoretical either. It's been caught in the act, once, in a modest 10-day brightening that nobody would have recognized without knowing what to look for. There's a related piece of evidence, and it's one of my favorite details in this whole subject. A white dwarf's enormous gravity should sort its atmosphere perfectly. Heavy elements sink out of sight within days or weeks, leaving only hydrogen or helium at the surface. So a white dwarf's spectrum should show nothing but the lightest elements. And yet a substantial fraction, perhaps a quarter to a half of them, show heavier elements: calcium, magnesium, iron, silicon, which means those elements arrived recently. Something is falling in. The interpretation is planetary debris. The surviving remnants of a planetary system, asteroids, comets, fragments of planets, are perturbed onto orbits that bring them too close, where they're torn apart by tidal forces and eventually accreted. Some white dwarfs even show disks of dust and gas around them, and a few show transits, objects passing in front, blocking light in irregular patterns consistent with disintegrating fragments. And here's the remarkable part. By measuring the composition of the pollution, astronomers can determine what those destroyed bodies were made of. The results generally resemble rocky material, comparable in composition to the Earth's crust and mantle. So it's possible to measure the geology of a planet that no longer exists, orbiting a star that has already died, by examining what's settled onto the surface of its remnant. Let's spend a chapter on a phase we passed over quickly, because it's visible from your garden. Stars in the late giant phases don't shine steadily. Many pulsate, swelling and contracting over months or years, changing dramatically in brightness. The prototype is Mira, in the constellation Cetus, whose variability was noted in 1596, the first variable star recognized as such, and named from the Latin for wonderful. It cycles over about 330 days, ranging from easily visible to the naked eye down to well below it. Amateur astronomers have tracked it continuously for centuries, and there are thousands of similar stars catalogued. The pulsation is driven by a valve mechanism in the star's outer layers. A layer of partly ionized gas becomes more opaque when compressed, trapping energy, which pushes it outward. Expanding, it becomes transparent, releases the energy, and falls back. Those pulsations are also how the star sheds mass. Each contraction lifts material outward, dust condenses in the cooled outer regions, and radiation pressure on the dust drives it away entirely. So the shedding we described, the process that eventually produces a planetary nebula, is powered by a slow rhythmic breathing that you can watch, month by month, with your own eyes. There's a related class of pulsator worth its own chapter, because it made cosmology possible. Cepheid variables are much more luminous than Mira stars, and they pulsate far more regularly, with periods from a few days to a few weeks, and brightness curves that repeat like clockwork. In 1912, Henrietta Swan Leavitt, working at Harvard examining photographic plates, deaf and largely uncredited during her lifetime, noticed that among these stars, the ones with longer periods were consistently brighter. That relationship turned them into distance markers. Time the pulsation, deduce the true brightness, compare with the apparent brightness, and you have the distance, which is how Hubble established that Andromeda lies outside our galaxy, and how the scale of the universe was first measured. And these stars are relevant tonight because they're dying stars. A Cepheid is a moderately massive star that has left the main sequence and is passing through a particular region of the diagram, a narrow band where the valve mechanism operates, on its way between burning phases. So the objects that gave us the size of the universe are stars caught in a specific brief, transitional stage of their ending. A chapter on the journey we mentioned at the very start, because it explains the structure of a star. Energy released in the core has to reach the surface, and there are two ways it can travel. The first is radiation. Photons absorbed and re-emitted by the material, diffusing outward in a random walk. That works where the gas is transparent enough for light to make progress, and it's what happens through the inner two-thirds of the sun. The second is convection. The material itself moves, carrying heat bodily. Hot gas rises, cools at the top, and sinks. The same process as water boiling in a pan. Where each operates depends on the opacity. If the gas is too opaque for radiation to carry the energy, the temperature gradient steepens until convection takes over. In the sun, the outer third is convective. The granulation visible on its surface, a pattern of bright cells about 1,000 kilometers across, each lasting minutes, is the top of that convection, with hot material rising in the centers and cooler material sinking at the edges. And which regions convect changes everything. Red dwarfs are fully convective, which is why they can burn all their fuel and live for trillions of years. Massive stars have convective cores and radiative envelopes, which is the opposite arrangement. So a detail about heat transport determines a star's lifetime, and therefore its ending. We've described red supergiants at length. Let's spend a chapter on what one actually looks like, because a few have been resolved. Betelgeuse is close enough and large enough that telescopes can resolve its disk, one of very few stars where this is possible. Images show it as a disk rather than a point, with visible structure. And that structure changes. The surface is dominated by a small number of enormous convection cells, perhaps only a handful covering the whole star, each one comparable in size to the orbit of Mars. That's utterly unlike the Sun, whose surface has millions of small granules. In a supergiant, the convection cells scale up with the star, so you get a few gigantic ones, each rising and sinking over years. The result is a surface that is genuinely blotchy, brighter in some regions, dimmer in others, changing on timescales of months to years. That blotchiness contributes to the mass loss, because a rising cell can lift material outward far enough for dust to condense, after which radiation pressure carries it away. And it appears to have contributed to the Great Dimming, a combination of a cool patch from a convective downdraft and a dust cloud formed from ejected material. So a red supergiant is not a smooth sphere. It's a slowly boiling, irregular, unsteady thing, shedding itself in patches and visibly changing shape over the course of a few years. One more chapter before the recap on how white dwarfs are used to date things. Because a white dwarf's cooling rate can be calculated, its temperature reveals its age. Find the coolest, faintest white dwarfs in a population, and you know how long that population has existed. The technique is powerful because it's independent of the methods used for ordinary stars. It relies on different physics, thermodynamics, and degenerate matter, rather than nuclear burning rates. Applied to globular clusters, it gives ages of 12 to 13 billion years, consistent with the turn-off method. Applied to the disk of our own galaxy, it gives an age of around 8 to 10 billion years for the thin disk, younger than the halo, exactly as the assembly picture predicts. And applied to the galaxy as a whole, it provides one of the independent checks that the oldest stars are slightly younger than the universe, which they must be. So the coldest, faintest, most inert objects in the galaxy, remnants that have done nothing for billions of years, turn out to be among the most useful clocks we have. There's something fitting in that. The things that finished first are the ones that tell you how long everything has been going. If you're still awake, let's walk back through it once more, gently, with nothing to follow and nowhere to arrive. It began with the warmth on your skin, and the fact that it was already ancient, energy released in the sun's core tens or hundreds of thousands of years ago, stumbling outward through a million random collisions before finally leaving the surface and crossing to here in 8 minutes. And with the observation that shining is dying, a star burns by consuming itself, and every star above your roof tonight is in the process of ending. Most will take billions or trillions of years. A few have only a few million left. Everything depends on mass. It sets the weight on the core, which sets the temperature, which sets the burning rate. And the relationship is steep enough that lifetimes span a factor of 1,000,000, decided at birth. The smallest stars burn so slowly and mix so thoroughly that they last for trillions of years. Not one has ever died. Every red dwarf ever formed is still burning, and will be long after everything else has stopped. A star like the Sun runs out of core hydrogen, contracts, ignites a shell, and swells into a red giant, engulfing the inner planets. Then a flash of helium ignition, so violent it briefly rivals a galaxy, and entirely invisible from outside. Then a second giant phase, pulsing every few thousand years, dredging carbon up from the interior and blowing it into space. Then the shedding. The envelope drifts away, the hot core is exposed, and its ultraviolet light catches up with the gas and lights it. A planetary nebula, misnamed by William Herschel in the 1780s because it looked like a planet through a small telescope. Beautiful, intricate, and gone within 20,000 years. What's left is a white dwarf, the mass of a star in a sphere the size of the Earth, held up not by heat, but by a quantum rule about which states electrons may occupy. It has no fuel. It simply cools for billions of years, eventually crystallizing from the inside out, which was predicted in the 1960s and confirmed in 2019. That's the ending for about 97% of stars, including ours. The heavy ones go differently. Their cores keep igniting, carbon, neon, oxygen, silicon, each stage shorter than the last, until the final day is spent making iron. And iron cannot burn. So the core grows until it crosses the limit, A 19-year-old calculated on a ship in 1930, and then it collapses from the size of the Earth to 20 kilometers in a quarter of a second. Electrons merge with protons. A flood of neutrinos escapes. The infall bounces and the shock stalls, and is revived by absorbing about 1% of those neutrinos, which is enough to blow the rest of the star apart. 99% of the energy leaves invisibly. We caught it once, in 1987. 24 particles across 13 seconds, hours before the light arrived. What's left is a neutron star, usually thrown out of its birthplace at hundreds of kilometers per second, or for the heaviest, a black hole. Sometimes with an explosion, and sometimes with nothing at all, the star simply vanishing from the images. And the debris carries the elements outward: oxygen, silicon, calcium, iron, into the gas, into the next generation of stars, into a cloud that collapsed 4.5 billion years ago, into a planet, and into you. Let me leave you with some things to rest your attention on. Not to learn, just quiet facts, true right now, while you lie still. 6,500 light-years away, in the constellation Taurus, a sphere 20 kilometers across is turning 30 times every second, as it has since Chinese astronomers wrote down a guest star in the summer of 1054, and its energy is still lighting a cloud 6 light-years wide. Around 1,000 other stars in this galaxy tonight, faint shells of gas are drifting outward, lit from within by the exposed cores of suns that finished thousands of years ago. Each one is a picture of what our own star will do. In the halo above and below the disk, ancient stars with almost no iron in them are burning quietly, formed from gas enriched by only 1 or 2 of the very first supernovae, and still carrying that chemistry on their surfaces after 13 billion years. In deep-sea sediment on this planet, layers of iron-60 are sitting where they settled 2 to 3 million years ago, delivered by supernovae a few hundred light-years away, close enough to leave a residue and far enough to leave nothing else. And in Japan and Italy and Antarctica, enormous tanks and buried arrays are watching for a burst of neutrinos, as they have every night for decades, ready to send an alert within minutes if a star in our own galaxy finally collapses. So here's where we stop. Every star ends, most of them quietly, swelling, shedding and fading into a small dense remnant that cools for longer than the universe has so far existed. A few dramatically, in a quarter of a second, after 10 million years of stability. And every ending is a delivery. The universe began with hydrogen and helium and nothing else. Every other atom was made inside a star and released when it finished, in a wind, in a shed envelope, in an explosion, or in the collision of 2 remnants long afterwards. Which means the carbon in your hands was made in the pulsing final phases of a star like the sun. The oxygen you're breathing was made in the last day of a massive one. The calcium in your bones came from an explosion. The iron in your blood came from a white dwarf detonating somewhere, billions of years before the sun existed. You are made from the endings. That's not a poetic framing, it's an inventory. Let your breathing get slower. You don't have to make it happen. It's already happening, on its own, the way it has all your life. Let your jaw loosen. Let your hands stay wherever they've fallen. Let the bed take your whole weight. Above the roof, a few thousand stars are visible, and every one of them is dying at its own pace, and none of them is in any hurry. And ours has 5 billion years left. Nothing is ending tonight that concerns you at all. Sleep well.